This is MrBean. MrBean is an Arch-any package for multi-environmental trial analysis. Today, before going into, let me check if this is moving. Yeah. Just to make sure that everyone is on the same page, I'm gonna introduce a little bit about the experimental design, how to compare different models, and also an example. I mean, then we will go to the application and we will see many things. I mean, single site analysis, multi-environmental trial analysis, and these kind of things. And as an introduction, so the experimental field is never completely homogeneous. That's something that we know. Even before the plans are established in the field plots, there is some level of variability in soil properties. So in addition, our traits can be affected by the management effect, and also the way that is applied the irrigation or the fertilizer can affect our traits. So that means that experimental units that are closer together tend to be more similar than the plots that are separated by greater distances. So this is more or less the main goal of the statistical analysis in the agriculture field. So we measure phenotypic responses. We have genotypic values and also the environmental factors affecting. So the phenotypic is the sum of these two different factors, the genotype and environment components. So what we try to do with the analysis is just to try to reduce the error and just to keep the what we need. I mean, just the genotypic information, like, let's say, clean. Just to give you an example, this is in the case of beans. This is an experimental unit. This is the plot with some plants. So this is basically the unit that we are going to measure. We are going to take the yield. We are going to take the days to flowering, the rest of the traits. And just to switch a little bit, let's say that this is an RCBD, for example, 2 reps. Because I mean, the focus of MrBean is more spatial analysis. So that means that instead of using this classical approach, rep, incomplete block, we are going to use the row and column information. So that means that every single experimental unit is going to be identified by the row and column position in the field. So this one, for example, is the plot in the column 1 and the row number 1. So every single experimental unit is going to be identified by the column and the row information. So in the model, I mean, what we are going to include is basically these components to model, or for modeling the spatial variation in the field. So this is just an example. Our phenotypic response is the raw data. Yeah. And let's assume that this is, for example, a photo taken by a drone, something like that, from the space. When we try this to model the spatial variation, reduce the residual, and just to get at the end just the genotypic blobs or the blues, let's say. There are different models. For example, I mean, in the way that we randomize, for example, completely randomized design, just the genotype, a randomized complete block design. We have an additional component here for capturing that variability, or to reduce that error, because that's something that we try to reduce as much as we can. Alpha lattice design. Now we have rep and also incomplete block. The error there, and the row and column information. For example, in this case, is the row and rep and column nested in the reps. And we can start like let's say combining things. For example, what if I put this component here, the block effect in the row column model, something like that. And the spots. This is not a randomization. This is more related with the way we analyze the data set. For example, we could have RCBD, but if we have the row and column information, we can analyze it using SPATs, for example. We could have an alpha design, and also if we have saved the row and column information, we can analyze it using SPATs approach. There are different ways to compare this, different criteria, AIC, BIC, R-square, irritability, residual variance. We can use it for comparing different models. And let's say, for example, the irritability is a good way to compare different models, for example, because this tells us about the proportion of the phenotypic variation that can be attributed to genetic differences. And this is an example that I'm gonna show you. I'm gonna stop here. Instead of showing the results, I'm gonna use MrBean. So this is basically what MrBean looks like. This is basically the interface. There is let's say a demo you can use basically without installing it in your computer. You can go just to this link and just start playing with the app if you want. But let's just introduce a little bit what the capabilities of MrBean. MrBean has 3 main, let's say, libraries for mixed model. SPAT, spatial analysis using spline. This is an approach that Maria Soxe et al. Proposed in 2018. ASREML, this is a licensed product, but it's pretty well known around SEG and the statisticians. LME4 is a free package that also helps us to fit linear mix models. And all of them are available in R, let's say. SPAT is for free, LME4 is for free. The one that is we have to have a license is ASREML R. But what can MrBean do for us? First of all, I mean, the way in which we import information, I mean, I have available an example data there, just for people to play with the app. We can import data set in CSV format, TXT, Excel files. And also, if you have storage information in BMS, for example, you can use it. Also BRAPI, for example, cassava base, sweet potato base, yam base, all these things, we can import data from those servers. Descriptive analysis, just something simple, scatter plot, box plot, distribution, mean, variance, coefficient of variation. And single-sided spatial analysis using this approach, SPATs. We can fit basically spatial analysis using these splines. We can get the blabs, the blues, irritability, identify potential streams observation, check the spatial trend, extract the variance components, and so on. Also, multiple sites, you know, is sometimes we don't have only one data set, but we have many. So multiple site analysis, I mean, in this case is a model for fitting multiple sites. In this case, I am not saying that it's an MET model because it's just to run it sequentially, one by one, let's say. Because this is, I mean, the application, I mean, the tool is taught for a 2-stage approach in the MET analysis, we will see in a minute. Yeah, so that means that in the first stage, we are gonna run or to get the adjusted means for each of the trials, and then we combine it in the second stage, but we will see. Multiple traits, spatial analysis for several traits. For example, let's say that I have one single trait, but of course, we measure many traits, days to flowering, days physiological maturity, yield, and other things. And we wanna see, for example, what is the correlation between each pair of traits. Outliers also, prediction by trait, Pearson correlation. And as I said, we also use ASREML. ASREML has a different approach for modeling the spatial correlation. They use this autoregressive correlation among the residuals. We use that approach for this. We can get the blows, irritability, check the spatial trend variance components. We can also use run replicated or augmented trials. You know, sometimes it's difficult in ASML to find the best model because, I mean, it's very flexible and we can use splines in column, splines in rows, a random factor in this way, direction, this additional random factor in this other direction. And we can start playing, for example, with these structures, autoregressive in one direction, autoregressive in the other one, the combination of both. So that's why we try to create something like this to select what is the best one using a REML. That's something I have to say that is something that we don't need to use in SPATs because I mean the approach is a little bit different, but we get almost the same results with the SPATs and REML when it comes to one single site analysis. The MET, we have a two-stage approach here. We can play with different variance covariance structures, factor analytic, unstructured diagonal, core H, core B. And also we can visualize some things using the principal components analysis. I also added like the traditional designs. I mean, RCBD, CRD, alpha lattice, resolvable or non-resolvable row column. And also we can get loops, irritability, and identify some outliers. This is for, so let's stop. I'm gonna stop here and I'm gonna jump to the app. Can you see my desktop? This is just to make sure. I mean, once we install the application, okay. Once we install the application, we can create like an icon in our desktop, just like this. I mean, in that way, we don't need to open our every time that we are gonna use MrBean. Just click on it, and then we will see something loading here. Yeah. Here I have the repo. This is available. I'm gonna share it with you through the chat. So just, but yeah, this is basically the interface. Once we install the app, we open it, we can see this is what we are gonna see. Basically, we have here all the models. This is the home, data, SPATs, ASREML, two-stage analysis, MET, traditional designs, and this is just information about the authors on the session, their session. Data, as I was saying, we have example data here. We can play with this data set. This is just one single site. We can import data set from CSV files, TXT files, all these things.
So first step is to get the data, Johan.
Sorry?
You're gonna tell us like step by step, right? First step is to get the data.
Yeah, exactly. Is to get the data. I mean, if we have already our CSV or Excel file, we can import it, just put it like here, and that's it, for example. We can also use, as I said, BMS connection. For example, if you have some information saved in BMS, for example, I'm gonna put my user here just to show you that we can use it just to get the data that we have storage in the system. Welcome to BMS. I have just access to beans. Which program? Let's say it's Uganda Kawanda beans. Which trial? This, let's check this one, preliminary trial, BEF. I think we have only one study here. Yeah, this study, and then we have to search it. I have to say that we are using QBMS. This is a perfect tool that helps us to do this kind of queries through the API. And in that way, we can have data like directly. I mean, we don't need to go to BMS, download information, then import it here. Just put your credential here, and that's it. This is for BMS, but for example, when in breed base, let's say, I mean, we don't need authentication in breed base, but we can use some of these servers. For example, Cassava base, welcome to breed base. And we have, for example, access to Cassava. Which program, I mean, it's up to you what you are gonna, um, you wanna analyze, I mean. But yeah, this is just the example data. I mean, I'm gonna use this one. Then we can move to the descriptive side. In this scattered plot, for example, is perfect for visualizing our experimental field. For example, this is the rep number 1, the rep number 2, and each of them. And then each point is a unique experimental unit, and it's basically our plot. We can see, for example, by line. Let me check. I'm gonna move this call row, and then the line, the name of the genotype, just to see where was located each of our entries. For example, this one. Oh, this genotype was located here in the rep number 1, in the rep number 2, in the other direction, and this is a different position. This is a check. This one has more replicates in the field, and so on. This is just basically to see what we have in the field for box plot. So if you wanna see what is, for example, the pattern in the field, I mean, you use your response and you plot it, I mean, against your column, your row, your rep, your incomplete block. Let me check by rep, for example. I mean, we can see, oh, okay, what is the median, the Q1, the Q3, the maximum, the minimum, so on. For example, yeah. And once we're happy with this, I mean, we can, of course, exploring more like with numbers, these statistics, for example. Let's see, for example, this is in this distribution. This is the distribution, for example, by rep. What is the distribution by rep? What is the rep, the mean, the standard deviation, the minimum? I mean, with the numbers here, with the table, I mean. And we can select, for example, okay, I wanna see what observation are here. I'm gonna put it here. Oh, it's crazy. That's it. Let me check what is happening.
Yeah, there might be a little bug there.
Yeah, probably. Oh my God, what is happening with this? But yeah, I mean, the idea is just to select like the top, something like that, just to see
and see the data
the
points.
maximum and the minimum and so on. Oh my God, where I go? Yeah. So yeah, probably there is a bug there. I'll solve it. I fix it in the future. But yeah, and that's basically the idea of this. And then we can jump, I mean, to spatial analysis if we want to use. I mean, I have to say that if we don't have a REML install, if we don't have a license, we cannot use these oral models. I mean, because of course they are gonna ask you for the license and for the. I mean, you have to have a license for this. I mean, in your computer. But if you don't have it, you can use, I mean, SPATs in this way. As I said, I want to show you, I mean, all the, let me check something here. Yeah, I just want to compare the different models. For example, in this case, I just have the response variable, the genotype. I'm going to take it as a random, and that's it. I'm going to feed the model. And we will see, okay, what is, this is our raw data, fitted data, residual. This is the environment. We are, in this case for environment, I mean, we don't have anything for, I mean, for controlling, let's say, spatial variability. I mean, we are not including anything here. So that's, I mean, that's a reason why we see these kind of patterns in the residuals. I mean, they should follow a normal distribution, independent in the field, and all these kind of things, the assumptions that they follow. But it's complicated because we are seeing a pattern here, and that's something that we have to avoid somehow. So that means that we are not modeling, the spatial variability. Here we can see what is the model that we are using in the ASRML syntaxes. We have the response, the genotype as random, and independent row and column information. It's just this. But the idea of this is that we can start playing with, what if I include the rep? For example, now we are modeling something in the field. This is the rep number 1, the rep number 2. But again, this is a pretty big experiment. And just by including the block, this block has a lot of genotypes, so it's difficult to model all the spatial variation that is inside. So, just including this block is not doing anything, basically. We have the same results almost. And we can see here that there is the readability. We will see this in a minute. What if I don't include this rep? The readability is 0.41. I'm going to include the rep. We will see that it increases a little bit, but I'm going to include the incomplete block because this is originally an Alpha-Laris design. I'm including this, the incomplete block. And we will see what is the model that we are fitting, basically the response, the block, the incomplete block. We have to make sure that this block is a complete block and this one is an incomplete block, And we are using the independent residuals. And we see what we are modeling. Basically, this environment that you see here is what we are modeling with the block and the incomplete block. Here now we have better behavior of the residuals in the field. That's something good. And the readability increase a lot, let's say. We can, for example, include the call and row if we wanna just explore what we are doing here. The readability increases. The readability increases. And like I said, the approach that we use in ASRML is using autoregressive correlation. In this case, I'm not using anything related with that yet. And we will see it because this is the spatial correlation. Spatial correlation, I'm gonna use the spatial correlation. That means that, of course, I am using a structure for modeling the spatial correlation in the residual. So that means that I don't have to worry about this because they are correlated, but it's because I am introducing correlation in between the residuals. And you see the readability is pretty high. Probably it's a little bit inflated, but we are gaining something at least. And we can, of course, for example, use the column, splines, include the nugget effect, all these things. And then basically comparing, the results. Diagnostic, and then we can just take, for example, what is the genotypic variance, something like that, and that's it. This is using ASRML. We fit a model, we can jump to see basically what are our predictions or our predicted values. And here we have, for example, this is the best one, this is the worst one, and so on. This is an histogram of the genotypic predictions. And here we have the table. We can easily download it here, just the predictions. And as I said, there is a different approach using SPATs. We'll see here, we have to select our response, the genotype. I'm gonna take the genotype as random. I have something here for checks. Because if your genotype, your checks are completely different from the rest of the population, we have to exclude them from the random part and to put it in the fixed part. This is just to do that. In this case, we have the call, row, rep if we want to include it, additional fixed random factors, a covariate, and then we can run basically the model. Here we have something, we want to remove outliers. If we found some. And here we have the output for spots. Summary, this is basically the plot, fitted spatial trend, raw data, fitted data, residual. We can see again the readability, residual standard deviation, and R square, coefficient of variation. And for example, this spatial trend, just to play with this spatial trend that we have here, but with more dimensionalities. And so yeah, once I run the model, I can go to the predicted values just to get what is, for example, the black or what is the blue of each of the genotypes that I have in the data set. Also the coefficients, if we want to go very, deeper, and to see what is the coefficient of each of the terms that we have in the model. Here we have the blobs as we saw in the ASRML model, histogram, prediction table, and histogram. And then also I have here this residual just to see or to remove. In this case, we didn't find something or strain observation, something like that. But we have here the histogram of the residuals against index, against fitted values, against, for example, let's say if I want to check, compare my residuals against the rep, just to see if something is not being modeled correctly or properly. For example, the call. With the residual, we can check if we are modeling everything or if we have to consider something extra or additional in our model. So that's pretty much about this model. We have also side by side. As I said, when we have multiple sites, so it's basically necessary to run many times the spatial analysis. Here I have, let me check. Here I have around 13 trials, I think so. We can check it here. For example, the yield, this is yield, and then we can go to data set, which is the one that identify our trials. Here we can see the behavior of the yield between all of them. We can jump exactly, just to the side-by-side analysis. This one could take some minutes, so I'm gonna just make a subset of this. For example, this, and this one. And let's include this one. I can go to side-by-side analysis. The genotype is the line. This is the way that we save this one. Experiment, data set, call, and row information. If I want to include something additional, info about the experiment, and then let's say that I'm gonna run it. This is the number of genotype in each of the trials. Shared genotypes, this is the amount of genotypes that are shared between each pair of trials. And also we can check the connectivity. We can see if all of them are present. For example, this genotype was just in this trial and so on. Then, we have to run this model. What MrBean is gonna do is basically to run each single site, and then it's gonna save all the results, the predicted values, the readability, and all these things. For example, here we run just 4 trials. We can see what is the genotypic variance, residual variance, correlation. This is just a phenotypic, a Pearson correlation. This is the summary, for example, readability for each of the trials, the genotypic variance. And also we can check like the spatial variation for all of them. But then once we, for example, in this 2-stage approach, we have to run the genotype as a fixed factor, as a fixed effect. Then we save the means, I mean the predicted values and their standard errors, and then with that is with those, I mean with that information, we go to the MET analysis. That's something that I'm gonna do. We go to the MET analysis and we import basically the results. This is something that I have here. Yeah, I think so. I mean, this one is just the predicted values. The genotype is our genotype, the experiment that you have, the trial. If we wanna select just a subset of them, we can do it here. And the weights, I mean, there are different ways to get these weights, but SPATS and ASREML provides you, I mean, using MrBean provides you like immediately once you run your model. But these weights are basically, they are using basically the standard errors. I mean, they are built with the standard errors. It's just 1 divided the standard errors, the square standard errors. But you can see, or you can find more information, like if you want to go deeper. Yeah.
Are you close to finish? Because we want to give some time for.
Yeah, exactly. This is the last thing. For example, yeah, I'm just gonna show the variances covariance structures, and that's it. As I said, there are different options to model this G by E interaction. We can use factor analytic, core age, diagonal, depending on the assumption that we wanna have. But let's check just factor analytic, and let's run. This is basically the same that I show you. Share number, and then basically we can check our model. I mean, we are using this factor analytic covariance structure. We can see what is the correlation between each pair of trial, also the covariance. We can download this kind of plots. We can see, for example, a dendrogram, just to see, for example, these 3 trials are more correlated than the other ones, probably because this is a different location. And for sure, this is a different location. This is Darien in Colombia, and this is a different location, Palmira, for example. And we can explore what is basically what we run, what we feed it. This is the syntaxes of the equation, let's say. If we want to get just the overall predicted values, that's it. If we go, for example, to the factor analytic, like the results, this is the genotypic variance. The variance explained by the components depending on the number of factors that we use. This case is a factor analytic 2. That's why we see 2 of them here. Percentage of variance explained. And for example, here we can see basically the loadings. Here in this side, we see Palmira, and in this other side, we see Darien, for example. We can find, for example, what is the best one. For example, let's say this one is the best one because of our correlation matrix, these kind of things. We can also use this latent regression to compare 2 genotypes. This is just for compare 1 by 1, something like that, because I mean, in general, we have a lot of genotypes, many trials, so it's difficult to read it sometimes. But yeah, that's something that we have available here. And just to close, I'm gonna, I mean, I have just the sources. I mean, different papers that I have used for building this. SPATS, for example, this book of genetic data analysis for plant and animal breeding, article of plant breeding selection tools, variance covariance structures. And that's it. That's pretty much it. I don't know if
no, that's terrific, Johan. Thanks a lot. Don't think that I wanted you to I didn't want to rush you. I just wanted to make sure that we have some time for questions. But no, that was terrific. I think you know, there's a couple of comments in the chat and questions
okay.
about, you know, more material for understanding how to run it. Of course, you know, we can see that you are very used to use the software, but some people would like to know if there is like videos or manuals, or where you can show, look, I don't know, a small video, single trial analysis, and showing how to do it step by step. And same with the installation. Gary was asking about just making it run, you know, just the installation and maybe a video for doing that. Is there any materials available, Johan, or plans to do it?
Yeah, for sure there is plan to do that, but I mean we don't have something available yet, because you
Okay.
know it consumes many hours
Yeah, I
probably
know.
to prepare this material, and also we have been working on preparing this. I mean, at least the manual, just the document. I mean, just a document with this step-by-step things. Because also the idea of making videos, it would be pretty nice to have some rep or something like that.
Yeah, I think so. Yeah, a series of maybe 5 videos where, short videos where the specific things are explained would be nice. Gary, I think you have a question. Please go ahead.
Yeah, this is beautiful. It's just perfect. Would you be able to take a few minutes, or can we schedule a separate session for installation and a little bit of a tutorial?
Yeah, for sure. We can schedule something. We can separate the space and then we can
And
try
could
to
you
install.
take 2 minutes now and just show us how to download it?
Yeah, for sure. I'm gonna take just 2 minutes. I'm gonna share my screen. Can you see my screen now?
Yeah, we can see it. So you go first to which place, Johan?
Okay, I'm gonna put this one.
In GitHub.
Yeah, in GitHub, I'm gonna just copy the link into
We can see it in the chat.
Yeah, perfect. Yeah, this is basically the repo. Here, you can see like the step is just one step, but first you have to go to R Studio if you have it. Studio. Oh, sorry.
But what you were showing that you had like a little icon, right, on your desktop.
Ah, yeah, exactly. But first of all, it's necessary to
Install R.
install. Yeah, exactly.
You see, that's the type of things that we need to probably
Yeah,
put in the
exactly.
video. Like, okay, probably you first install R, then you open R, and then you install the GitHub.
Yeah, exactly, because that's the first step. Once we have installed R, we go to basically the script. And you copy and paste this code that is available here. Yeah, remember that if you don't have these DevTools installed, you have to go to
you have to also
packages, install. Yeah, exactly, DevTools, and then sorry, install this package here, DevTools, like that, and that's it. And then we copy and paste this one here. Okay, using
type enter.
Yeah, type enter, and then we have to wait a couple of minutes. If it's necessary to update, I'm gonna say that I don't need to update anything. But I mean, the first time that you install, for sure, if you don't have some of the packages, you are gonna need to update all the packages that we are using or that are needed for running MrBean. But yeah, but by clicking 3, I mean, I just omit. I mean, the updating all of them, and that's it. I mean, you have to wait a bit more.
Kit,
And
do you want to
then
ask something on what he's doing, or do you want to wait until he finishes?
It's a separate question.
Okay. Then let's just wait for Johan to finish this one.
Okay. So the first step, install packages, packages, DevTools, like this. The second step is to run this line, and that's it. Library and run app. You will see in a minute. Just that's it.
Okay.
Then it's gonna open like in your browser.
Could you just put all those steps in the chat?
Yeah, for sure.
Thanks.
And we have also the recording, Gary. So in case you want to see it again. So Johan, and let's say that it opened the browser, but
yeah,
then,
exactly.
But then you said that you could also bring that icon to your desktop.
Yeah, exactly. I'm gonna I have to create this step by step, like inside the README in MrBean.
Okay.
But I mean, I have this MrBean like create an icon. It's
Create
just
an icon.
to copy and paste this piece of code, of course, and you will see. You put it here in R. You copy this line. I'm gonna close this, but then I'm gonna just run
Create
this
a
piece of
shortcut.
line, and then you exactly you define where do you want to save your icon, something like that. For example, in desktop, let's say I'm gonna
Yeah, if you want, you
make
can
a
put in
new
a different.
folder, for example, and
Yep.
test, and I'm gonna put it exactly test. Okay, and that's it. We go
If you
to
go to
test.
folder test, it should be
Yeah,
there.
exactly. And then here it's here, and you can send it to
the desktop.
the desktop. Yeah, create icon. But I already have one, so I have now
Yep.
copies of
That's
them.
great.
But yeah, this is more or less the step by step. But for sure, I have to prepare like a piece of
No, yeah.
manual.
I think a video, probably you can explain it in 10 minutes, everything together. Hopefully we can convince Steve to steal some days from your FTEs and FTE and then develop some of these videos. Good. Kit, please go ahead.
Yeah, sorry about the accidental early hand raising there. I just had a question about heritability. So these different methods and models use different heritability estimates. Have you standardized it to only use one estimate? And if so, whose estimate are you using?
Okay. The heritability that we are using, and I think it's pretty well known. The college heritability is the one that we are using across all. I mean, even in the last site, in the last model that I didn't show you, is for classical designs. I'm using also the college heritability. I mean, also for SPATs is using the college heritability, and also for ASRML are, I mean, it's just the same one, just to make sure that everything is comparable.
Okay, great. Thanks. It looks really good.
Yep.
Thank you.
Yeah, the college heritability, I think, is becoming the standard. That was a good question. Johan, there is also there was a question on the data that you were showing. I don't know if this is very relevant, but they were saying that in the row column plus IB design, there were two rep effects, one in red and another one in blue. Are they different reps or the same? Do you know what does that mean? Or
okay. In the roll call incomplete block, there were I think it's in the presentation. It's during the presentation, and I'm gonna put it. It's during this slide, I think so. Yeah. That's a good point. This should be the same color, but it's because this is not this is a different factor. This is the row nested in rep. So this is a completely different factor that this is just the main effect of rep. So that's why I put it in a different color, but it's the same rep, basically. It's just with a different color because this is a different term. This is the row nested in rep and the call nested in rep. Yeah, exactly, in rep.
So Johan, another question was, on the connection to different databases. What exactly people can do if they want to connect to their specific database? Let's say some people were asking about EBS. What is needed? Do we just need to get some of the EBS people and then sit together with them and make the connection, or how that can work?
So I think if we have probably an API, if EBS has an API, we can easily connect it, because I mean, through R we can create all the paths. I mean, the URL, the connection, because that's something that we did with BMS. I mean, BMS, they have an API, so it's pretty easy to go to R and to get data. Also in Cassava base, all these kind of things, they have also an API. So I mean, I mean, it was pretty easy to go to. I mean, I started with BMS, but once we realized that basically the calls, they collect calls, were basically the same. We said no, it's basically the same, and that's something that, for example, the package, this QBMS, can help us to do it. I mean, it's pretty much because they have almost the same calls, so it's easy to get data from this repo, from this API, but it's because they have APIs. I don't know if EBS has an API also.
I actually don't know if there is an EBS person in the meeting. Maybe not, but if there is someone, please jump in and let us know. But I think that was one of the biggest issues at the beginning.
Yeah, I think there is a good question. There is another good question in the chat.
Gary, you want to
It's
say something?
about-
Because I can see that you.
No, just it's critical that the EBS be linked through an API, presumably through RAPI to this. So if this is not high on their to-do list, it needs to be put there.
Yeah.
I see a different another question.
Yep.
Can you explain why irritability increase as you include reps and block effect? Look at this. This is the model comparison. Here I have CRD, RCBD, alpha, row, call. I mean, this is the way in that I analyze the data set. I mean, I have one data set. But I analyze it in different ways. For example, I include the call, I include the rep, I include the incomplete block, I include these nested factors, and include these combining things. It's just the way in that I analyze the data set, because it's originally an alpha lattice design, but I analyze it in different ways. And you will see here that, I mean, we are reducing the error. I mean, by introducing the rep and also the incomplete block. So somehow, if we reduce the error, I mean, I'm gonna use this just very quick. For example, irritability. If we take the basic one, bare genotypic variance divided genotypic variance plus bar error divided by the number of reps. Let's say that we use this one. If we attacked, let's say if we reduce this residual error variance, for sure we are gonna increase this irritability, because we are reducing this term somehow. So with these terms, I mean the row and column, also the rep, the incomplete block, with those factors, we are basically reducing the error, experimental error, and in that way we can somehow improve our irritability. I don't know if I was clear or I get you confused more. But yeah, that's pretty much it.
Yeah. It's very, your explanation is very clear. As you know, what do experimental designs and spatial analyses do? They move spatial residual variability, out of the noise category and into the signal category. So we increase the we increase the relative size of the genetic signal to the noise that's left. And that's, that happens also as you increase the number of replicas.
Exactly. That's a good point. Look at this.
Good.
Thank you. Yeah, good.
All right. Is there any additional question or comment? Like I said, Johan, let's talk to Steve to see if he can allow us to steal at least one or couple of days to make these videos. And to be honest, I have also talked sometimes to the EBS people about integrating some of the tools that already exist in the CG. But I think the main challenge that they see is that that connection or the back end, they feel that it sometimes is not as straightforward. That's why they are trying to build from scratch some of these things. I guess that, to be totally honest, I'm also not a software development or developer expert to really, say what is better. But I think it's very valuable that they also understand that there are some tools within the system that are already well developed, and they can actually accelerate the use of some tools, especially for our breeding programs in the NARS. But yeah, we'll see. So Johan, thanks again. Hopefully, like I said, we can follow up. And
Yeah,
if
for
there's
sure.
any additional question or comment, please just drop an email to Johan. I'm sure that he will not be upset if he
For
receives.
sure. I'm gonna put my email in the chat. Yeah.
Yeah.
So yeah, thank you everyone. Thanks for being very active.
Yep.
And yeah, thank you, Eduardo, again for having me.
Yep. Good. Okay, take care, everyone. Thanks for joining and have a great day. We'll talk soon.
Okay, thank
Bye.
you.
Bye-bye.
Thanks, bye.
Bye. Thank you very much.
Bye.
Take care.